Well, good evening, everyone, and welcome to the 2013 Ottawa Centre Annual Dinner. Apart from our lecture by Dr. Jenna Irvin, your experience of combination of astronomy and gastronomy will be to the hilt. And diets are out the window. Check them out the door, please. No diets tonight. The food is fantastic. Who's the first time eating at this buffet? First time? Oh, you're going to want to come back, folks, I'm telling you. For sure. Well, towards the end of the evening, of course, there'll be awards handed out for deserving members in their fields, and as well as lucky door prizes handed out over here at the table. Well, the Ottawa Centre has had a great year in monthly meetings, star parties at CARP, and various outreach programs such as schools and other events such as Fun Fest, and there are a few others which I can't name right now. And we have a few dedicated volunteers that have spent many hours away from the families and friends to popularize these events. So could those volunteers please stand up so we can thank you for your time away from home? Who's been at outreach? That'd be you. That's Brian. Thank you, Brian. Great. And we have many more. Joe, stand up. Joe, stand up. Just stand up. You did one. All right, Joe. Yeah, Joe. Yeah. Okay. And we have many more that did not come to the banquet tonight. Well, the Ottawa Centre has also started some groundbreaking work, thanks to Eric Kujala, in streaming our first monthly meeting on the internet. To date, 312 people have seen our first meeting on November 1st, either live or replayed. In fact, the meeting at the live night, I was also on the computer chatting with some people in the room, and the furthest were California and Hawaii watching live. So my goal, hopefully, yes, yeah, round of applause for sure. Thanks, Eric. So my ultimate goal in astronomy is, for outreach, that is to get the centres online, hopefully all 29 centres eventually, through the help of Eric, to they get on Newsstream.tv. I mean, this is outreach to the hilt. Imagine watching a Vancouver or Victoria night or St. John's. Be just great. Well, oops. No, it's not a Foster Brooks thing, believe me. In 1868, our society sprang into the roots by a very small group of friends that formed the Ottawa Astronomical Club. By 1900, several communities were affiliated with themselves along with the club, and the numbers grew. Well, fever also ran high with the visit of the Duke of Cornwall and York. So in January of 1903, a petition was drawn up and forwarded to King Edward VII to ask for the prefix of royal to be added to the new name of the society. And on March 3rd, that petition was granted, and the Royal Astronomical Society of Canada was officially incorporated. So with that tradition in hand, and accepting of the royal family, let us raise our glasses. Stand up, please. Raise our glasses. To the Queen.
What are you standing for?
And if we can please remain standing and lower your glasses so we can commemorate Remembrance Day this past Monday for a moment of silence for our fallen comrades and those still serving to protect our great country. Thank you. You may be seated. Let it be known, folks. Let it be known. Loud and proud. Loud and proud. And now I call upon Chef Gordon to take us into the gastronomic experience. Take it away, Chef.
Ladies and gentlemen, good evening. It's my pleasure. Hello.
You tell he's a teacher.
Thank you. Good evening, ladies and gentlemen. It's my pleasure to welcome you here one more time to Algonquin College. And it's always a pleasure having you here. I can tell that Christmas is just around the corner when I do the Royal Astronomical Banquet. And it is true, Christmas starts next week. Now that the Independence Day is over, we get ready for our holidays. And at this time, I'm going to say to you, because I'm not going to see you again until next November, so I'm going to wish you all the very best during the holidays, and hope that the new year brings much joy and prosperity. In saying that, ladies and gentlemen, I'd like to ask you to remain seated. I will go from table to table, at which time I'll invite you to our lovely buffet here this evening. Our chef, Brendan, was instrumental in preparing your meal. And like anything else, you ask the chefs to do something, they always do it their way. Brendan is no different. Brendan is a member of the Federation of Ice Carvers, and he did, if I can have normally we like to do a hip of beef for you people, and tonight being a smaller group than normal, doing an 85-pound hip of beef would be a little excessive. So we weren't able to do a large one, so we did what we call the top round of beef for you this evening. But there's lots to go around. Brendan was instrumental in preparing your meal, and I said he used a chainsaw from a 300-pound block of ice. Now, he only had 2 minutes and 30 seconds. This was already carved prior to this evening, so Brendan had to jump on me. So when I got out there to time him, he was finished. Brendan uses a chainsaw, and this is the outcome of the chainsaw. Now, ladies and gentlemen, remember one thing. You are not in grade school, or some students today in high school. So you may come and touch this ice carving, but please do not put your tongue up against it. Of course, you know Canada spans from coast to coast, and this represents our beautiful country of Canada. Up here we have what you call the Pacific Ocean, which means that's a Pacific salmon up here, and of course the lower section is the Atlantic salmon. There is a big difference for most of you, I'm quite sure know, there's a difference between Atlantic and Pacific salmon. We have what you call the red salmon and the pink salmon.
Sense of direction.
At the far end of the buffet table, ladies and gentlemen, I ask you to refrain from starting at this end.
Except for the president.
Except for the president. No exceptions. You will start, well, fine, if you would like to start at this end and use this as plates for your main course. No, you will start at the very far end and you will conclude at this point, or this point if you so desire. And then later on, once you finish your main course, after you have finished 2 or 3 times in the main course, and you would like to come for dessert, feel free to make your way up at any time. Coffee and tea will be brought to your tables. Those of you who do not know where the washrooms are, as you go out these doors and you turn to your right, you go right to the very end of the hall, make another right, and you walk right into the men's washroom. You go around that wall, then you'll find the ladies' room. So you can escape from the men's washroom. Any questions, feel free to come back and ask me, and I'll direct you exactly where to go. Enjoy your evening, ladies and gentlemen, but remember one thing. It's a lovely evening, it's an evening of celebration, but I must ask you, ladies and gentlemen, those of you who are driving, I would like you to be extremely careful with your drinking this evening. Many people on the streets tonight, one drink can create a problem. Please have your eyes directly in front of you and behind you to watch all directions on your way home. I'd like you to enjoy your family. Thank you very much. Have a lovely night.
Want me to cut it a little bit?
Yeah, let's do a little, let's get the juice in there. There we go.
Get a little action shot, yeah?
See him sitting there at home and reading it. 1905.
Yeah, the Conservatives weren't in power long, but they did a lot of damage.
But they normally sold it for 67 years. How you doing?
Hey there.
They're both going to be retired, so, you know, it looks a little bit actually not too happy.
Okay, folks, we'll start round two. Did everybody enjoy their fine feast? Excellent. I hope Chef heard that. Chef, did you hear that? It's like this for people the first time. It's like that every year. It's just fantastic food. So I hope you come more often. So without further ado, I'd like to call up our Vice President, who is in charge of this entire shindig. It's always the duty of the Vice President to set up the annual dinner, door prize, whatever. So everything is on Gordon's back. Please welcome our Vice President, Mr. Gordon Webster. That's it, Webster. Yeah. Hi, I'm Gary.
Hi,
nice to meet you.
Nice to meet you. Almost blew it there, Gary.
Good evening, everyone. On behalf of our president, Gary Boyle, and the rest of the membership, it's my very great pleasure to welcome and introduce our special guest speaker this evening, Dr. Judith Irwin. She's a professor in the Department of Physics and Engineering Physics and Astronomy at Queen's University in Kingston. It's also a great pleasure to have Judith's husband, Dr. Richard Hendrickson, here with us this evening. Dr. Hendrickson is a professor emeritus in the same department as Judith and a world expert on magnetic fields, hence the attraction between the two. So welcome, Richard. It's also a delight to welcome Judith's brother, Bob, and his wife, Marg, who live here in Ottawa. Welcome. Now, I don't want to tell tales out of school, but I heard a story of how, as a teenager, Judith would visit a friend whose house backed onto a golf course in their suburban Winnipeg home. And she would go out in the golf course after dark and lie down and look up at the stars to be away from the streetlights. So how was the view of the Milky Way from the third hole? Not bad. Dr. Judith Irwin completed her Bachelor of Science degree in mathematics at the University of Winnipeg in 1975 and her master's degree in astrophysics at the University of Victoria in 1978. From 78 to 1980, she worked full-time as a physics lab instructor before launching into a 3-year tour as a planetarium instructor with the Mobile Planetarium in Alberta. In 1983, Judith left her Dome Roman days behind her to begin a 5-year period of study culminating in a PhD in astronomy at the University of Toronto. During her time at the University of Toronto, she also worked as an observatory tour guide at the David Dunlop Observatory. Dr. Irwin came to Ottawa in 1988 to work as a research associate at the NRC's Hertzberg Institute in Astrophysics before taking up her position as a professor at Queen's in 1991. Dr. Irwin's research interests include the interstellar medium in galaxies, the galaxy disk halo connection, outflows from active nuclei and disks of spiral galaxies, and galaxy formation and interaction with the intergalactic medium. In 2002, Dr. Irwin gave a presentation at this dinner on galactic structure. I can't say enough about how thrilled we are to have her back with us this evening to present Pushing the Radio Limits, New Glimpses of Galaxy Halos with using the expanded Very Large Array. Please join me in welcoming Dr. Judith Irwin.
Well, thank you very much. I knew I had been here before, but I couldn't remember the year. And then I was told that you keep a record of all this, and I was quite relieved to realize that the title is actually different this time than in 2002. Also, thank you, Richard, for being here with me over there. So he's the theorist and the smart one. So if there's a really hard questions at the end, I'll just point them that way. And also thank you to Bob and Marg for being here, who came basically to mock me. Actually, my brother did. My sister-in-law is too nice for that. So, so anyway, it is a delight to be here. And I thought today I would talk a little bit about the radio sky, which is a little different from what you look at normally. Give you some of the whys and wherefores, why we do it, etc. And then introduce a project that I'm quite close to, working on very hard, and show you some early results from that. Okay, so let's see if I can work this. Okay, so the first question is, why bother with radio astronomy? And some of the pictures I'm showing you now of galaxies will show up again later. So you might like to remember a few of them if you can. So this is NGC 3079, and it is a spiral galaxy, like the Milky Way, but it is edge-on to the line of sight. And so the spiral structure you can't see very well, you just see kind of a line in the sky. Now, this is the only graph I'm going to show you, so don't worry. I'm not going to show you a lot of graphs.
We love math.
But I have to show it to you because this is the spectrum of this galaxy, this particular galaxy. So what it is, it's a plot of the brightness of the galaxy, the actual, we call this a flux density, as a function of frequency. So what do we do here? We, if you were to take a sort of circle in the sky around this galaxy and add up all the light, you would get a number which is called the flux density, and it's usually in units of Janskis or millijanskis, and that would give you 1 point on the graph. And so the optical would be all these points in here. You can see the error bars are a little bit high, but these are the optical points from this galaxy. So in fact, this is a Sloan Digital Sky Survey, so it's supposed to be kind of close to true color, but as everybody knows here, the colors are somewhat enhanced in this picture in comparison to what you actually see through a telescope. Okay, so the optical region is just this little part in here of the spectrum. And what are you seeing mostly with your eyes is starlight. Almost entirely starlight. There's a little bit of ionized gas emission in optical and so on. And so you would get your points in here if you did that little adding up. If you had then an X-ray telescope and pointed it at this galaxy, you would find some points down here, and this is what I'm calling exotica. It means in the X-ray you're looking at very high energy phenomena like pulsars, like the accretion disks around black holes, like binary star systems, and so on. So there are very specific kinds of objects which form your points in this region if you took a picture of the X-ray and you added up all the light. Now over here you'll see there's a really big peak in the infrared. And that is actually reprocessed starlight. So if you can see the galaxy, you can actually see some dust lanes along here, just a bit of a faint one. But there's dust throughout this galaxy. And the dust will absorb the starlight, the optical starlight, and re-radiate that light in the infrared. And so it's actually reprocessed starlight that you're looking at in the infrared, mostly. In fact, the Earth does the same thing. The Earth absorbs our sunlight in the optical and re-radiates in the infrared. So the Earth is really just a big, giant dust grain. Okay? That's what we are, a dust grain. So here's the radio. And you can see that it's quite different. And I'll talk about a little bit more about it in a minute. But you've got this sort of slope here. So it sort of starts down here and goes all the way up in this direction. And it does its own thing, completely different from what the starlight is doing, or the infrared, reprocessed starlight. And in fact, we don't even know what happens down here. This is low frequency, and the reason is because the radio waves can't make it through our ionosphere down to the ground. And so in order to find out what's here, you have to put a telescope in space. I mean, that's true for X-ray and ultraviolet. You see, there's no ultraviolet in here at all. But in the radio, you'd have to put a very, very big telescope out there, and I'll explain that shortly. So there's a lot to be known down here, and we just don't know. This curve has to turn over at some point, or else the energy would be infinite from this galaxy. But this is what I would like to focus on mainly today. So why bother with radio? The first reason is energy. If you restrict yourselves to the optical, you really have a very tiny view of what the galaxy is like. Okay, now, there's another reason, several, but I want to focus on this one. And my guess is that there are people here who know what this is.
Salamander.
No.
I've seen.
It's a very old photo. It's an old radio photo from the VLA in the early days. I think it's from 1990 or something like that. No? Well, it's old in terms of the VLA. Does anybody know what this is? Okay, I heard it. It's Jupiter. That's what Jupiter looks like in the radio. Okay? Now, as you can see, it's very, very different. So what's going on? Well, Jupiter has a magnetic field, as does the Earth. And you can imagine a sort of dipole around it. There's Jupiter. And Io is the innermost of the Galilean satellites. Many of you have seen it, probably everybody. And Io has a lot of volcanic activity, and it contributes a lot of particles. And those particles stream in its orbit around Jupiter, forming this strong sort of, or this denser region of material, basically, ionized particles. And so if you look at it edge on, you can see a very bright spot here about where Io is, but there's more stuff around it as well, because there's magnetic fields, and we know that charged particles are sort of bound to magnetic fields. Electromagnetic radiation comes from that. So of course the Earth has the Van Allen belts as well, so the Earth has something similar. What's going on? Well, basically for radio astronomy, we are looking at electrons. We are looking at the emission that's given off by electrons that are spiraling around magnetic field lines. And the strongest emission from such an effect comes at radio wavelengths. Now, if the electrons are not relativistic, then it's called cyclotron emission. And the cyclotron emission from the planets usually occurs at a very, very low frequencies. In fact, sometimes below that ionospheric cutoff, so it's very hard. You can't even measure it from the Earth. You've got to have your satellites and so on. But if the electrons are relativistic, approaching the speed of light, then you get what's called synchrotron radiation, and that is also strongest in the radio, and it has a very specific spectrum, a very characteristic spectrum that you can, and that when you see it, you know it's synchrotron radiation. So there are two ingredients. If I see synchrotron radiation now, there are two ingredients. You need high energy electrons, which are actually the electron component to cosmic rays, in fact, and you need magnetic fields. And so even if you don't see magnetic fields or measure them directly, if you know that there are if you've measured the synchrotron radiation, you know they must be there, and you know that the high energy electrons are there too. Now there are high energy protons as well, but they don't emit, at least not. They're actually a very negligible emission in comparison to what the electrons do. Okay, so the other reason that I'm focusing on for radio is that the content and the structure of what you see in the sky is very, very different in the radio. It looks different, you're looking at different things, you're not looking at starlight. Okay, now, overall, the strongest radiation in the radio wavelengths in our universe is synchrotron radiation. And I'm just going to give you an example here of Centaurus A, which is a nice elliptical galaxy with a very strong dust lane across its center. And this is an active galactic nucleus type of galaxy. Okay, so here is an image of the same galaxy, and it's an optical, and so the purple here is the radio, and then there's an X-ray part as well. And you can see that in the radio, you're picking up jets that come from the core of this galaxy and form two blobby lobes on either side, and this is all synchrotron radiation. So even though you don't necessarily have a map of the magnetic fields, you know that they must be there, and you know that the energies are high. What's making this? Well, there will be a supermassive black hole in the center of this galaxy, as we think there may be in almost all galaxies, in fact. And the region just around that black hole has a huge amount of energy and strong magnetic fields. And if you have sort of accretion along this direction, you can imagine two jets coming out with the disk itself holding things back in that direction and allowing the jets to fly out in this direction. This is the same galaxy. This is Centaurus A, and this part, which is over here, is down in this region. And you can see that if you can push your limits in the radio and look fainter, you see much more. There's always seems to be more to find. This is an enormous jet, which has sort of gone out in this direction now, but probably was pointing in a different direction in the past. And so this stuff that's farther out was ejected a longer time ago, and the angles are a little bit different. I'd love to show you this picture because this shows you how big this thing is. That's the full moon, and this is to scale. So you can imagine if our eyes were sensitive to the radio, that you would have a completely different view of the sky. It would not look anything like what we see with our eyes now. Okay, so what about radio emission from a normal spiral galaxy? I showed you a very specific case with a very bright double-lobed jet and so on, but what about a normal spiral galaxy? Well, we're in one, okay? So we're in the Milky Way, and if you're not used to this kind of projection, we're here, where are we? We're looking towards the center of the Milky Way in this direction, and then this would be 90 degrees one way, this would be 180 degrees around, so it's like you'd have to wrap this around you, so it's galactic coordinates. And then this would be the North Galactic Pole and the South Galactic Pole. So this is actually a whole sphere which has been flattened out in a sort of map. And you'll all recognize a beautiful optical image of our Milky Way. This is what it looks like in the radio, 408 megahertz. And I think you'll agree it's rather different. Remember that we are looking primarily at synchrotron radiation. Is there anything else in there in the radio that's emitting? The answer is yes, but the fraction of the brightness, the fraction of the emission is actually low in comparison with synchrotron emission. So there is some emission in here from just hot gas, 10,000 degrees Kelvin or so. And if you were to tune your radio telescope to exactly 21 centimeters, you would look at the H1 21 centimeter line. But unless you're tuned to that, this is not what you're seeing. Again, we're looking at essentially magnetic fields and cosmic ray electrons. There's our friend Centaurus A that I just showed you. That's where it shows up. And I wanted to point out now these weak extraplanar features. So you're looking away from the plane, and there's all kinds of arcs and features that look rather faint, but nevertheless are real, and I'm just pointing to a few of them. And so the extent of the emission that you see out of the plane is much greater than what you saw for starlight. It was just basically confined to the plane. So let's consider what this means. There's a small picture I'm starting with here. So this is just a picture of the Milky Way, and here's where the sun is, way in this little square in here. So we're 8 kiloparsecs from the center, 8,000 parsecs times 3, about 25,000 light years from the center of our Milky Way. And if you blow up that little part really big, you get the bottom picture here. So the galactic plane goes along this direction, and perpendicular to the galactic plane is up and down in this direction. Now, we happen to be in a local, what's called a local hot bubble. So we're talking here now about gas, and we're not talking about starlight anymore, but the sun is in a sort of evacuated region. Now, of course, all of this is very much close to a vacuum, okay? Even the densest molecular clouds have densities which are much less than you can make in a vacuum on the Earth in a laboratory. But the line of sight is so long that it's actually quite easy to detect this emission, okay? So this particular emission would be, this would be a molecular gas of some kind, and then very low hot gas here where the sun is. And this is actually just an artist's sketch, okay? It's kind of hard to do this, to get this map out. But what's the point here? The point is that you have a disk, and then you have these regions where the sun happens to be, in fact, where there's a lot of stuff going up and down out of the plane, just like the image I just showed you. So there's actually material that is cycling up and possibly down and leaving our Milky Way in a fashion that is rather interesting and possibly affecting our sun. And in fact, I don't know what effects that might be. It's a whole new area that hasn't really been explored yet. But I find the time scales rather interesting because we know that these features, when we see them in other galaxies, they are features that are perhaps tens of millions of years old, which isn't that long, isn't that old. So tens of millions of years to form such a feature, and maybe it lives for that long. But if you compare that to the time of the revolution of the solar system around the galactic center, that's about 250 million years. So the sun will have gone around the Milky Way center, 10 times or so during the short lifetime of these things being formed. So the sun could have gone through a number of these things, denser material, lighter material, less dense material, and so on, in the course of its revolution. Ditto the age of life on Earth. For about 3.5 billion years, there's been some kind of life on Earth, and that's much longer than the time it takes the sun to go around the center of the Milky Way, and again, much, much longer than the time scale for these features. So the point I'm trying to make is that we live in a rather dynamic place. The Milky Way plane is, the stars are going around, and we know that there's a lot of dynamics there as well, but the gas, and in the case I'm going to be speaking of more, the magnetic fields and so on, it's a very dynamic place. There's stuff going up and possibly stuff coming down, circulating. There's stuff leaving, perhaps, the Milky Way. And there are implications for that in terms of the amount of gas that would be left for, say, forming the next generation of stars and so on. So what about the big picture? Now, the big picture is very hard to see from inside our Milky Way. So it's very hard actually to map out the Milky Way. It's like mapping out a forest from inside it. So the better thing to do would be to look at other galaxies and see them as a whole, and maybe galaxies like our Milky Way. So are other spiral galaxies like the Milky Way? So let's take a look at a couple of examples. Looks like some aren't. Here's an example, and this picture was taken at the Very Large Array, of which more soon. This is a galaxy that doesn't seem to have much of any. Now I'm looking at synchrotron radiation again. It just seems to have a point source at the nucleus. It's just an active nucleus at the middle. This may not look like a point source to you, but that's just because of the resolution of the telescope that took this picture. And some are. Here's NGC 3079 again, the one I showed you right at the beginning. It is this edge-on spiral, and all these contours here represent synchrotron radiation seen at radio wavelengths, in this case using the Giant Meter Wave Radio Telescope in India. And I'd like you to just look at this for a while. Suppose you didn't have any optical information, and all you had were radio. There would be no such thing as a disk galaxy if you looked at this. It would just be a huge roundish blob. It's as far up or down out of this disk as it is across. It's almost elliptical were it not for the fact that there's structure on all these scales. So in fact, if you change the resolution of your telescope and look with more finer and finer detail, you see more and more and more structure. There's all kinds of structure inside there. So what does this mean? It means that there must be magnetic fields around this galaxy that extend as far out as the radius of the disk. Okay, so there's quite a contrast between these two galaxies, right? So, in fact, I can tell you that it looks like more galaxies are closer to this than they are to this. It's come to the point where we've looked at this and think this is the unusual one. But we don't know for sure. And the problem is that these halos are actually pretty faint, and it's hard to observe them. And so our information is rather patchy, and we don't really have a good survey or a good feel for what most galaxies actually do on these scales. So what can we do? How can we get the data? So we have a window of opportunity. The Very Large Array is in New Mexico in the USA near Socorro, south of Albuquerque. And it's now called the Carl G. Jansky Very Large Array, but it has been commonly referred to as the expanded VLA, and it's undergoing a huge upgrade right now. Now, the expanded Very Large Array is a bit confusing because the telescope itself, there's a railway track here and along here, and so you can actually expand and contract the whole array for reasons I'll explain in a second. But that's not what's meant by the expanded Very Large Array. What's meant is that it is expanded in frequency. And the goal is a continuous frequency coverage from 1 to 50 gigahertz in the radio regime. So I've put these two bars on the last graph that I showed you. Actually, I lied. I said that was the only graph. No, it's not a lie because it's the same graph. Okay. So the goal of the Very Large Array is to have complete frequency coverage between these two bars. Now, this may not seem like much on this picture, but believe me, this is a huge expansion of frequency coverage compared to what we have had in the past. And, I have to mention, there's my little flag. I spent $2.99 on that flag to get the But the reason is because the whole reason that this can be done now is because of a correlator that was built in Penticton, BC. And that correlator is now in place at the Very Large Array, connecting all these, it's the brains of the whole thing. So it's connecting all these antennas together in an intelligent way. So it allows this kind of wide band. So it's called the wide-R correlator. Now, what's the point here? The point is that not only can you have complete frequency coverage, meaning you can focus on this on the left-hand side. My hand's got to be straight and here it's shaking too much. Or you can point it here, or you can point it here, or you can point it here, and you can set your frequency anywhere in that band. But in addition, the band itself can be wide, and if the band is wide, it's equivalent to adding in surface area for sensitivity. By increasing the band width, we can increase the sensitivity by about a factor of 10, which is actually a big jump. And in any improvement you get in instrumentation that's by a factor of 10, pretty much guarantees you're going to find something new in astronomy. So everyone's looking for that magic number. So instead of doing the very, very expensive thing, which is to add more and more and more of these antennas, the cheap thing is to increase the frequency and allow you to actually observe at any particular frequency with a wide bandwidth. I just thought I'd mention a little bit as to how this is done. At radio, the radio regime has wavelengths that are much, much greater than in the optical. So if you want to match the resolution of an optical telescope and look at the fine detail, you need to increase the size of the radio telescope. In fact, you need to increase it by 400,000 times in order to get exactly the same kind of resolution, kind of detail. So how do you do this? To make it sort of short, imagine yourself standing on an astronomical object looking down on the Earth, the way we're looking right down in the VLA right now, and the VLA is watching you, and tracking you over time. And the Earth is turning while this happens. And so a little bit later in time, the whole array will rotate with respect to the astronomical object. And then a little bit later on, the array rotates again, and then it rotates again. And in my original slides, I had sort of transparency, so you could see all the different orientations of the array. But now what you can imagine is that rather than having just this much of a width to give you the resolution that you want on your astronomical object, your resolution is as if you had a synthesized aperture this big. And as time goes by, all those other rays sort of fill in that big aperture. So, it's it would cost a lot of money to build a huge radio telescope this big, but you can more or less get the same resolution by putting all these together and allowing that rotation to occur. So this is aperture synthesis, it's called. Okay, so where does this leave us? Now, I would like to introduce our program. It's called Changes. It's Continuum Halos in Nearby Galaxies, an EVLA survey, and then they changed their name officially to the Carl G. Jansky Very Large Array, rather than the Expanded Very Large Array, which totally screwed up our acronym. But so now when you write your paper, you have to explain that in the first sentence. But anyway, people sort of understand now. So this is we started this program at this sort of window of opportunity now that the VLA is really enhanced and has come online more or less to offer these new opportunities. And so this is our group, at least it was our group. We've got a few more people added since this picture was taken. But we have almost 30 people now, and these are disk halo experts representing 7 different countries. And we've come together to investigate this disk halo phenomenon on the large scale, to try and see them in other galaxies. And so there's one guy who's over there. He's canoeing down the Yukon River. Okay, isn't that great? And these people are experts in various fields. So we have people who are experts in the X-ray, experts in observational magnetic fields, expert in cosmic rays. So we've tried to represent all the wave bands, but the particular focus of this project is to use this expanded very large array to see if we can do better than has been done before. Okay, so here actually is our first paper. This is our logo, which was created by J.Ann English, who's at the University of Manitoba, and it shows our 35 galaxies, all edge onto the line of sight, and there's a sort of shape here that's meant to represent the Very Large Array, its configuration. Okay, so what are we trying to do? Here's just a few. This is the list of our galaxies, and here's a few images for you. First of all, we want to map the cosmic rays and the magnetic fields at the interface between disks and halos in the IGM. What do I mean by halo? When I showed you NGC 3079 a while ago, the halo would be sort of the broad scale around, the emission around the galaxy. The disk halo interface would be sort of the region that's close in to the disk, just in that transition between the disk and the halo. And the halos in the IGM, this would be the intergalactic medium. So beyond the halo, there would be an even fainter intergalactic medium that you might see in some cases if you have the right information. And we want to search between the links between halos and underlying star formation rate. Now, one of the ideas is, of course, that you've got to form these conduits, and you have to make these features that go up and down out of the plane. How is that done? And star formation seems to be something that people have focused on, and there's good reasons for that. But when we say star formation, we really mean a supernova rate, because when stars are forming, there will be massive stars forming, and those massive stars will turn into supernova, and it will happen on short time scales compared to the age of, say, the sun and other stars. So there should be, and there does appear to me, a relationship between the extraplanar features and star formation rate. However, it doesn't explain everything. there are cases in which outside of the star-forming region, like maybe out here, you still see some features that come out, and they can't be easily explained by star formation alone. And this is why we think that magnetic fields may be very important, because there's enough energy and pressure in those magnetic fields to assist or to possibly even act without star formation in order to create these features that go out of the plane. So we want to search between those links, and we want to understand the energies and the mass loss rates, whether the mass is lost completely, whether it comes back, et cetera, et cetera. And there are some other goals that are somewhat more esoteric. So where are we? Just to say where we are in our program, we are observing at 2 different frequencies, 1.5 gigahertz and 6 gigahertz, and we're observing in 3 different arrays. So what that means is that very large array could expand along its railway tracks, and when it expands to the largest size on the ground, it gives you the finest detail on the sky. And if you compress that array on the ground, you can observe cruder spatial resolution on the sky, but you get more flux or more brightness in that pixel, if you want to call it. So there are benefits to going to the squashed and the stretched arrays. And B is the most spread out. Actually, there is an A array we're not observing yet, but B for us is the most finest resolution, then C, then D. And we're using C and D at 6 gigahertz as well. And all 4 Stokes means basically that you're looking at total intensity, but you're also looking at something called Stokes Q and U, which give you polarization images. And the polarization is what will tell you about the magnetic fields. Okay, so we're actually getting, so you can see that we're going to get 1, 2, 3, 4, 5 maps for any galaxy, but we do observe with different, there's a ways to weight the array. So we actually can get 2 different resolutions for any given setting. So that would be 10. And then you have I, Q, and U for each of those. So we're getting 30 maps per galaxy. And that's actually not all of them. There are some others that are called spectral index and so on. So I'm working up to explaining why it's so hard to get all these data together. My husband complains all the time. Just give me the result. Okay, so we've got 405 hours on the VLA, and the first 3 papers are now published. And we are going to release, this is a sort of legacy value. It's called a large proposal on the Very Large Array. It has a so-called legacy value, and we will be releasing the images to the public when we're confident that they're all, that we're happy with the way they've come out, hopefully within a year for the first ones. We've got all the data, and about 2/5 have been processed. Now, remember I said that everyone's trying to save money by, instead of adding on more antennas into the array, which is very expensive, you want to increase the bandwidth. But what you end up with is a huge expense in software and in manpower. And I can tell you that this is not trivial to reduce wideband array data. And I'm not going to go into all those details because it's kind of dull. But I will, give you one reason why it's not trivial. And this is it here. Now, when we first get the raw data, before you actually make a map, you plot, I did lie after all, this is another graph. Okay, you have a plot of the amplitude, which is related to the brightness in the sky, as a function of frequency. Now, this is the band, okay? This is what I'm calling the wide band at one particular point in the radio. So this is just raw data before you do anything with it. So now you see something interesting. There's a bump here, a little bump at the end. There's a very tiny bump right there. There's a huge whopping bump there, and there's another one in there. And it's all interference. Aircraft, GPS, GLONASS, radar, iridium, weather satellites, cell phone towers. All of it is interference. The real signal is way down in there. That's what we want. And now you're going to say, come on, get an algorithm to search through and do it all, get rid of it for you. And we've tried, and there are automatic algorithms that we've tried, but they simply do not do as good a job as doing it by hand. So we do spend a lot of time excising interference. That's what the same data set looks like with the interference gone. It's not calibrated, but you can see that this big chunk had to disappear. Various other chunks, this one here was bad, had to go, etc. And there's a lot of experimentation involved as well, because interferometers, like the Very Large Array, were actually originally developed to get rid of interference. And because you're looking at what's called a correlated signal. So what it tends to mean is that the worst interference is seen at short baselines, the two antennas that are close together compared to the two that are, say, far apart. And so there was a bit of experimentation that we had to do for a while to see whether you might be able to salvage the wide baselines and throw away the small ones, whether that would do. And to make a long story short, when it comes to external interference like this, you usually have to throw everything away. This test data really helped us because we actually, for the real data set, we actually managed to avoid, we reset the band so that there was actually a gap right here, although we did still end up with some tail end interference in almost all our data sets at this particular band. So there it is, that's life. Okay, so I'm skipping all the other things, but let me now just talk a little bit about what we have found. And as you know, we haven't finished all the data reduction, but I'll show you a few results anyway. Actually, there were some unexpected surprises. And this galaxy is quite interesting. It's a beautiful edge-on galaxy, beautiful dust lane right across the middle, close to 90 degrees. UGC 10288 at a distance of about 100 million light years. And I'm not sure if anybody noticed, but there was actually a press release about this yesterday. And it shows up on the astronomy. I'll show you in a minute. Just keep on going. This, go on and on about it. This is the previously known radio image of this galaxy, okay? The previous radio image that was taken, the only one, in fact, ever taken of this galaxy before our data, looked like this. It was just a kind of a blob. In fact, there's a bit of an elongation to the north. This was taken in 1991. And it almost looks like it could be an error in the data, the way it appears, but there is an elongation to the north. So what do we see? Same galaxy. This is what we see. Remember, we have 30 images, so I'm picking and choosing amongst them. But here's our radio emission in contours. Synchrotron again, magnetic fields, cosmic rays, electrons. And there are features that come out of the plane, which are real, up and down, that are associated with this particular galaxy. But there's this huge object right over here. And when, I guess I should mention this, when I reduce the data, you don't have all the overlays at the time. All you're doing is looking at the radio data. And so I couldn't see the full extent of the disk at that point. I saw some disk emission. I saw this stuff, and I thought, oh my goodness, this is a double-lobed radio galaxy in a spiral. That's very unusual. So I was really excited about it. Then I did the overlay, and I said, oh, wait a minute. This is not centered on the galaxy. This nucleus would be there. If it's a double-lobed source, it would be centered on the nucleus of the galaxy. There's a bright little optical dot right in the middle. There's another one over here. It's fainter, but it's there. Then you start looking up some information, and you find that this is actually a background quasar. So I thought, oh, wow, what are the chances you'd have this amazing alignment perpendicular to the disk of this background source with our galaxy. So we've nicknamed these two guys, Sauron and Saruman. Although in the scientific paper we had to call them changes A and changes B. But we didn't. I almost sent it in with Sauron and Saruman, but I thought, okay, if I was the referee, I probably would say don't do. The interesting thing is that when we chose the 35 galaxies to begin with, we had a lower flux density cutoff. In other words, we didn't want to just take anything. We picked galaxies that we knew had some kind of flux from a previous measurement. And this galaxy, were it not for the background source, this galaxy wouldn't have made the cut. We've now realized that the brightness is mostly from the background, and this foreground galaxy would not even have been in our sample, because it's a very low brightness, low flux density galaxy. So this is what I meant to from yesterday. This image was formed by J.N. English, who is in our consortium. And it's a superimposition of the same two galaxies, but with different bands and different resolutions. And it's in the Astronomy magazine website, and this is the NRAO website, so it comes up in a few places. Now, you might think, okay, this is an interesting little superposition, but so what? And so after my original excitement and then my disappointment, I was excited again because Richard and I chatted about this, and we realized that the background source was actually a probe. The light from the background source is a probe of the foreground galaxy. And you could do some really neat science with this. So let me try and explain why. So this is a quasar, it's double-lobed radio jets. It's about, by the way, over 6 billion light years away compared to the 100 million of the foreground galaxy. So it's like 62 times farther in the distance. Now, the light from this galaxy, from its upper and its center and its lower lobe, is actually polarized. So it's the same kind of thing as your polarized sunglasses. If you have a light source, you have, think of it as a wave now, and you have stuff going up and down, up and down, up and down, up and down, and you have side to side, side to side to side to side waves, and everything in between, and that would be unpolarized light. And now if you pass it through a filter of some kind, in this case like a picket fence, then you block out the side to side, side to side light, and only the up and down makes it through. And so this light is called polarized. So the stuff from the background galaxy is polarized, not 100% like this, but there's polarization involved. Now, the foreground galaxy, I'll just try and press the button again. The foreground galaxy, we know, has a magnetic field. And we don't know whether there's a magnetic field in the halo or not. We don't actually see the halo, because it's, except for the features I showed you in the previous image that showed some rather discrete features, they were there. But what happens is, if polarized light, polarized up and down like this, passes through a region with a magnetic field, and the magnetic field would have to be an aligned magnetic field, like one that's along the line of sight, then the output will be rotated. So you see this arrow is up and down in this diagram, and then you pass it through a magnetic field, and then it rotates a bit, like that when it comes out. That's called Faraday rotation, after Michael Faraday, the English physicist. Now, the amount of rotation is different at different frequencies, and we have lots of different frequencies within our band and between our bands. And so what you can do is analyze the extent at these frequencies to which the background source has a rotation of its vectors, and that gives you information about the magnetic field in the foreground galaxy. It's really quite a great tool. And so far as I know, that hasn't been done before for anything quite like this. So we have done a preliminary analysis, but the full analysis is yet to be worked out. It's being worked on now, in fact, by others in our group. But the interesting point is that even though this emission in the front is so faint that you don't necessarily measure it directly, you know it has to be there because of the effect that it has on the background galaxy. So that is, I think, scientifically a really, really interesting result, and we're looking forward to doing more with that in the future. Okay. Let's try another galaxy. So this is one that I have just shown you before that has this point source in the nucleus, and this was also an unexpected result. First of all, you do usually see some kind of emission from the galaxy. You don't usually see just a point in the middle in the radio, but in this case we do. And not only that, but it's variable. What does that mean? It means that if you go back to the archives and look at the VLA survey from what year? Late 1990s, and look at the flux density, that point that you would put on that plot, and compare it to the flux density that you're measuring now, you see that there's been an increase of a factor of 5. And not only that, but our data, because we observed in these different arrays, we observed over a period of maybe 5 months. You know, you might have an observation, 2 months later you get the other array, blah, blah. In fact, maybe longer than 5 months. We even see a variation over that time period. So we seem to have caught this. This is some kind of an active galactic nucleus, probably related to, I guess, a supermassive black hole in the middle. And we seem to have caught it at some kind of period in its outburst. And in fact, after I put this slide together yesterday, in fact, we had a telecon amongst our group. And I was mentioning that there was a strong, what we call circularly polarized signal in this galaxy. It looked really interesting. We needed to follow up on it. And someone, you know, is at the computer on the telecon typing it in and coming up with the fact that there's an X-ray outburst from this galaxy too, which occurred about 5 months earlier than our observations. And so, in fact, it turns out that this is some very active nucleus of some kind. We don't know exactly what kind, but now there's some kind of confirmation at X-ray wavelengths as well that it's an active nucleus. So that's something that we will pursue as well. Sorry.
I don't mean to interrupt, but in the previous slide,
Yep.
that lobe that extends to the upper part of the galaxy, can you see those rotational aspects in the upper part of that lobe, the lower part of that lobe versus the upper part?
You see a difference, yes.
You do?
Yeah.
You have
Now,
a resolution for that, right?
yeah, because the Faraday rotation down here will be much greater than it is higher up. Now, in fact, preliminary results suggest that there isn't any Faraday rotation right up here in this lobe, which cannot be explained by a foreground screen within our own Milky Way. But the other points down in here and down here, they differ from each other. So it's almost like you can do a kind of 3D imaging. You can really understand what's going on.
Thank you.
Okay, so here's our variable source. There isn't much more to say about it because we haven't gotten very much farther except to say that this is what we've got so far. Okay, the other interesting result we're finding is some uncovering hidden structures in polarization. So here's a galaxy, NGC 5792, and it looks very nice here. In fact, here's a background double lobe source again, right there. You're seeing a lot of background sources. This one's not close enough really to the galaxy to tell us much, but yeah, the contours are the radio, so you start to see a kind of a spiral pattern. There's some radio emission along here. Now, if you look at the polarized light, we're overlaying the contours of the radio. Otherwise, you're looking at optical, okay? So it's an optical image. This blue image is optical as well. But the polarized light, what is it? It's a point source in the middle and 2 little lobes on either side. They're not little, but they look little in the picture. Now, you can see that there are lines across these lobes, and those lines tell you the direction of the ordered magnetic field in the galaxy. So that is a product of our survey. With the polarized emission, you can get the direction of the magnetic field. So that's coming out as well. And I'm getting towards the end of our results now. So these are a few images of some other galaxies we've found. I just thought I'd throw them up for you. Again, the colors is an underlying optical image. The contours are radio continuum, so that will be synchrotron emission contours. And the red bars are the magnetic field direction. So in fact, you can think of this as like if you lie a magnet on a table and you sprinkle iron filings on it, they line up along the magnetic field. So you can think of these little lines as being like your iron filings, showing you the direction of the field. And in general, you find if you look way down in here, the lineup is right along the disk. But as soon as you walk away from that, you get all these fields going in directions away from the disk. So it's just a confirmation in a way that stuff is going up and that magnetic fields are involved. To the extent we have to do these calculations and figure it out, but the magnetic fields are likely a non-trivial component in the ejection of the material. Here's another one, NGC 5775. I'll show you this one again momentarily. This has a lot of specific structure that go up in specific regions. Now, you'd want to correlate this with where active regions are in the disk, where there'd be star-forming regions in the disk, or whether there wouldn't be. This correlation hasn't really been done yet. Here's another one, NGC 4157. This has a huge halo, which I'm not showing you in this picture, but the optical image is here. And there's your iron filings, if you want to call them that, your magnetic field direction. In fact, this one looks like there could be an enormous loop here, but that has to be confirmed with a bit more data reduction. And there's NGC 660. And again, optical. The contours here are the radio synchrotron. And there's structure again there. And there we have our magnetic field direction. You see, it's pretty complicated. But again, this goes along the disk pretty much in here. But then you start moving away with very specific regions where, so it's this dynamic sense of the fields, the dynamic sense of the disk-halo interaction that it really shows. Okay, so where are we going from here? First of all, of course, for our project, we need to finish the data reduction, and we need to start addressing very carefully the goals that were set out at the beginning and eventually release the images. But I thought I would just end with a few ideas to ponder. None of this has been through a referee, but I think it's a very interesting comparison to consider. Back to NGC 3079. Here we have our edge-on galaxy. These are all our magnetic field lines. And look in the middle, this is right in the nucleus. There's a known to be an active nucleus here, kind of a outflow region. So the black and white is actually H-alpha, so it's an optical image. And the iron filings here are forming a nice loop in this direction. If you just follow the magnetic fields, they sort of close, beautiful little loop, like so. Does that look familiar? This is the solar prominence, which we know without a doubt to be formed in relation to magnetic fields, very strong magnetic fields. And we know that these show you the magnetic fields right there. So we have a magnetized bubble at the nucleus, and I'm just comparing it to what you see on the sun. The difference in scale is somewhat amazing. On the left-hand side, this sort of feature is about 200 billion times larger than the feature on the right. But we still believe that physics is the same on the Earth as it is on the sun, as it is in the rest of the universe. And so we don't believe there's anything that there necessarily has to be anything wildly different about the physics. It's just hugely different in size. Back to NGC 5775. Here is just a radio image, and I've turned the galaxy on its side here. And it's at a particular resolution that shows you lots of detail in that sort of disk-halo interface. And the one on the right is the same galaxy. That's a gray scale, is an H-alpha, so it's optical. And the contours here show you the broad scale halo around the galaxy, although the resolution is not great in that image. So here are some solar prominences. And look at this, there are very great similarities. As I say, there's high energy particles, there are magnetic fields. We may be seeing something that's similar. And so it may be time to think of gas and galaxies as we do with the sun. So there would be a photosphere meaning a disk, and there would be a chromosphere, which would be our disk halo interface, and there would be a corona, which is a large-scale halo. So rather than looking at a very small scale on the sun, which we know is not small, but compared to this, the whole galaxy may be doing something similar. So we do know that magnetic fields is the missing ingredient, and there have been a few patchy surveys in the past, but there has been nothing done that's systematically looking at the magnetic field. So that's actually the unique property of this particular project that we're working on. And so Changes is starting, we hope, to fill in the gap. And that's all I had to show you. Thank you.
Optically, we see galaxies have a blue shift and red shift, but in radio, do you see that too?
If you look at a spectral line, you do. In the continuum, you can't see it, because what I mean by that is I showed you that graph of just all this line of radio emission. If it were to shift a little bit to the right or to the left, you couldn't tell. But if you look at the 21 centimeter line of neutral hydrogen, which is in the radio, it has a specific rest frequency, and then, yes, you can certainly see red shift and blue shift. Or other lines, like there's an OH line at 18 centimeters. There are a few other lines in the radio as well. Okay.
Judith, if I can bridge your two presentations from 2002 to today.
Oh, no.
Well, back then you were pushing for, when we look at galaxies in the optical, they appear a certain way. So you're talking about the Hubble classification system for galaxies and how inadequate it was. Have you been continuing to push to, obviously we see galaxies in new light, say, right? What have you been doing? Have you been pushing that as your pet project forward at all? Or?
I'm actually amazed that you could tell me what I said in 2002. I have.
Full disclosure, it was Tim Cole who reminded me. You like the slides?
Yes. Well, I'm not doing too much in that. There is one student that I co-supervise at Trent University, whose main supervisor is there, who is doing some work on galaxy classification from the point of view of large data sets. It's more a computing kind of thing, but it's still in the optical. Although what we're trying to do is include. You have a sort of parameter space that you're trying to probe to understand what the galaxies are. We're trying to include some of the other parts of the spectrum in that, but I haven't pursued it much more beyond that point. It's actually a very difficult problem. If you think of the history of observational astronomy, optical astronomy goes back to Galileo. Radio astronomy goes back to, at best, 1939 or something, Karl Jansky, right? And X-ray astronomy is a space age, and UV astronomy and gamma ray astronomy all have to be done from space. So I don't think we just don't really have the data sets. What we really need is nice, evenly spaced data across that whole spectrum, and then we could push for the kind of classification you would like. But we all look at these things. We're used to the optical with our eyes. We're used to spirals. We're used to ellipticals. So remains to be done. Yes.
Two questions, if I may. One to follow on the redshift bit. The pictures you were showing where there was the background quasar at 6 billion
Yes.
light years distance, presumably the radio waves that were coming through would have started out being closer to optical or something like that. But I'm guessing that doesn't matter because it depends what they are when they pass through the foreground galaxy.
Okay, the distant 6 billion, previous to our observations, all you saw was that little optical dot in the middle. That's all that we knew of. And so the redshift of that galaxy was determined optically. And it's not really a true redshift, it's what we call a photometric redshift. So how can I explain that? There's a lot of information of galaxies in the distance that you have proper redshifts for, meaning you've measured a spectral line. And then you have a whole bunch more that you don't, but you have colors. And by looking at the ratio of the colors, you can correlate that with a true spectroscopic redshift and conclude that just by measuring certain colors, that would give you the redshift. So the background galaxy we have a photometric redshift for, which most people would believe more or less. Now, what would it have been emitted at? Yes, it would have been emitted. So we don't have a spectral line, we just have colors, okay? But it would have, when you see it in the optical, it would have been emitted in, say, a UV or something. But I'd have to work it out. I mean, you can work it out. It's delta lambda over lambda naught is V over C, which is Z, right? Delta lambda over lambda naught is Z. We could work it out after, where it would be in the spectrum when it had been emitted before we actually got it, received it here. So the optically, the foreground galaxy, I don't think is doing much to that. It's in the radio that we're seeing this Faraday rotation. That's where we're seeing the difference. I don't know.
Just a technical question. With your radio now, how close can we get radio-wise to the optical spectrum?
Can you see us getting a full spectrum of radio right through optical to X-ray in the future?
Yeah. You know, the NGC 3079, the first spectrum I showed you, the thing is, I don't know if I can go all the way back. Is there some way to go right back to the second slide? There's nothing much that's preventing us from getting anything at any of these other data points other than time and money. So all of this can be done from the ground. Beyond the ionosphere, you've got to observe from space. Now, that we don't have the technology for. I think probably you'd want to put a radio telescope on the moon.
Assuming we have.
Yeah, you could fill in the whole spectrum, but the UV, there are UV data points for other galaxies. This one doesn't have any, but we have have had UV telescopes, one called FUSE, for example. Galax was another example. So all of these could be filled in, but what we find is that this is typical of any spiral galaxy. It's kind of interesting. You could look at the Milky Way from a distance. You'd get the same kind of spectrum. You'd look at M82, M81. You see almost exactly the same kind of shape. Now, it might be a little bit higher, a little bit lower in some places, but they all essentially have the same kind of thing. So if you were trying to argue for a new telescope to fill in the dot right there, the committees would say, why don't you just draw your line? you know, I mean, you have to, it's just one of these things where you can argue, but there's no reason why you couldn't fill in the whole thing. Yeah, I mean, there's all these are radio points right here.
Yeah. I'm just thinking of radio right through the optical.
Yeah, we don't quite know where this bottoms out. That is a bit of a gap right now in our knowledge. But the technology is there to fill in that gap from space, not from ground. Yeah.
Yes, just a different kind of question about how you organize this project, because how on earth does one get 405 hours of time on VLA and pay for it?
VLA time is free.
I want some.
It's not an easy task. It was quite a job putting together. Like all time on the VLA, you have to propose for, and it goes through committees, and it goes through referees, and it's discussed and ranked, and so you have to make sure you're high ranking. In this case, there was a category called large proposals, so we put in for that. And if I had done it on my own, I wouldn't have gotten the time, even if I had a bunch of graduate students who could do all the data reduction. I wouldn't have got the time, because the strength was, I think, largely on the strength of the whole group, including Richard and the magnetic field people in Germany and everybody together whom we had, we'd known each other scientifically, we'd read each other's papers, so we sort of knew who the community was. And we thought, if we're going to get all this time, we better get together and do it together. So that's what we did.
So the operating costs are paid for by the National Science Foundation, I guess? Or something?
Yeah, it's... NSF, I don't think, is the only...
Okay. And the instrument that was made in Penticton?
Yes.
Who paid for that?
We did. You did. Canadian taxpayers paid for that. But I mean, it was a very high-tech instrument, very something we can be proud of. Many people were trained and learned on this to high technological levels, so I think it's something to be proud of.
Is there another project that's hogging time on the VLA? Like, what's the big project that's eating up VLA time?
There's quite a few now. Well, we're finished, the observing. If you go, there's a public site called nrao.edu, and somewhere in there you can click to large projects and find the other ones that are in the works. Yeah.
Last question.
I was recently reading about the latest observations. I think it's the Planck telescope and cosmic background.
Yeah.
And apparently they finished their data collection a year and a half ago, but they're only publishing the results now because they had to do, I think, something similar to you, which was get rid of all of the noise between the cosmic background and what they received on the telescope.
Yeah.
Were the kinds of algorithms or issues they faced all similar? I guess they didn't have to worry about cell phones.
I think they're more worried about, I mean, this is infrared, right? So they're worried about dust between themselves in the background and dust in galaxies and how to account for that. Radio waves go through just about anything. I mean, aside from their effects like these Faraday effects that I mentioned, but they pass through, wherever it is, they pass easily through whatever is between us and them. Our problem is more, I'm not sure which problem to mention. There's so many. But it's when you collect the data on the ground, you're dealing with multiple interferometers, and I'm not sure if you're mathematicians in the crowd, but we do a Fourier transform. It's a mathematical function that relates what's on the ground to what's in the sky. Then we have to correct for the fact that it's not a huge circle that's filled in that you're getting. There are spaces between those antennas. That's producing problems you've got to correct for. The problems are different at different frequencies, so if you have a wide band, you have a different effect here than out there on that side. There's a field of view which introduces issues. It's so sensitive that if you look at an object here, like a Virgo cluster, I'm sure many of you have observed galaxies in the Virgo cluster. We have several galaxies there. A good example is NGC 4388. And M87 is a very strong radio source. It's way, like 6 primary beams away, and it will still wreck it'll still cause problems. It's like light leaking or something across your field of view, and you have to find a way to get rid of that. So those are more technical things like that we have to worry about.
Thank you very much. We have a small token of our appreciation. Thank you very much for your wonderful presentation. Sorry, he wants us to
Okay, so thank you, Dr. Irwin. That was an excellent talk. Opened up new visions on how radio astronomy really works. Now we'll call up our meeting chair, Paul Collinger, to give away some awards. And as Paul heads up to the stage, this is Paul's last meeting with us pretty well. Paul's retiring from being meeting chair, and next election we'll have a new one. This opportunity, I'd like to thank Paul for all his work as meeting chair, and also Chris Tarrant too, and Louisa. I'll get back to you in a minute. First of all, you don't know, but to put our meeting together, it takes these guys about 2 hours the night before the meeting to get all the slides together. That's done every month, 2 hours of their precious time. Thanks, Louisa. But also on thanks to Chris and Louisa for offering their house when we have our council meetings. The cookies, you can't stop at 4. The coffee's fantastic, and we do actually get work done. So again, thanks for opening up your house. A round of applause for these three great people. Thank you. Okay, Paul, so come and take it away. So yeah, these meetings are running pretty smooth, almost as smooth as silk, or as smooth as...
Thanks, Gary.
Okay,
I'll remember
two
that.
words again.
Well, I have to give you a slight correction on what you just said about me doing all the hard work and Chris too. No. It's completely the opposite way around. These meetings, our meetings, wouldn't happen without Chris, or at least nowhere nearly as smoothly. He makes the job of chair. For those of you considering the chair in the future, he makes the job of being chair incredibly, incredibly easy. So again, a big round to you, Chris. And then, of course, there's Louisa, who plies us with cookies and other refreshments so that we can do all our hard work. So.
And also as secretary too for our center, extremely great work in
Absolutely.
anything that I need from Chris, he's like 30-second email away pretty well.
So Chris, if you ever want to quit the RASC, it's not going to happen. Sorry, that's just not going to happen.
We're going to have to double his salary next council meeting.
That's right. I'll second the resolution too. All right. Anyway, one of the reasons I'm up here is it's my pleasure, as it was last year, to provide or to announce 2 awards that we like to give away annually. I'll make sure I got the right ones here. Okay. Okay, right. Thank you. And I don't want to drop them in the process. Okay. I know that one of the recipients is here today. I don't believe the other one is there, but I will announce it. So I will announce both. And if I'm sure if the other recipient isn't here, I want you all to, we will announce this again at the December meeting for these awards there. But we'd like to kind of keep it for a bit of a surprise for the other recipients. So I will announce the first one here. The Paul Commission Observer of the Year Award, which we've been giving away for just a couple of sessions now. This is given to somebody that's demonstrated a propensity for extreme observations, not only getting out into the field and doing observations, but meticulously keeping track of what they've done, recording their observations, and really taking a scientific approach to it. The recipient of this year certainly well earns that, and my hat's off to him as well, because while he's doing all these amazing observations and recordings, he's also finding time to empty beer cans and make cameras out of them. So without further ado, Observer of the Year for this year, Mr. Rick Wagner. Thank you. Yeah. Sorry?
See the logs there, they're amazing.
Oh yeah, you've got them there. Yeah, I have to. I was amazed when you sent your data, Rick. I went through that stuff and do you sleep much or?
Not this year.
No? Yeah, I could tell. Rick, very extensive notations there, observations of even the minute things that he's observed there. So very professional approach to keeping logs, and I really commend you for your diligence in recording information at that level. That's the mark of a true scientist, I think. So, job well done. So the other award that I'd like to give out is. This one I have sometimes I had a hard time last year as well, because we have so many good presentations over the course of over the year. People that are coming up for the first time to give presentations, people that are seasoned pros at it and can do very slick work. But this year we had a rather interesting one, and I think I know some of you would have seen that. The award this year goes to John Wayne Ross for his talk on Planets of the Gods there, which was I thought it was a rather interesting talk. It was a little bit different than the kind of stuff that we've had or that we typically have. It wasn't technical. It wasn't. It was astronomical, but it wasn't super astronomical. It related sort of archaeology with science, with astronomy, and I thought John just did a really remarkable job on this. So he had some good competition, but the choice of graphics that he had in it, and just the way the presentation flowed and some of the conclusions that he came to, I thought he did a really good job. And I know unless I haven't seen him all night, I don't think you're here, John. We will award this to John at the December meeting, but even in his absence, I think we owe him a round of applause there. Thank you. So again, mum's the word, okay? Try to not let the cat out of the bag there, because we want to see his expression. Mr. Boyle.
Thank you.
Hand it over back to you.
Thank you very much. So congratulations to Rick and on their awards. Also, I'd like to thank Ann and Art Fraser when I was passing out thank yous. Ann and Art Fraser, every month they're passing out coffee and soft drinks and cookies, so a round of applause for them too. Over 10,000 sold up to now, over 10,000 sold. Great.
Before I go, I have one last thing I must do, and that is to thank someone who helped me enormously throughout this whole process, and without whom most of this probably wouldn't have happened, and that's Brian McCullough. Thank you, Brian. I'd be lost without you.
Thank you very much, Gord, and thank you, Brian, again for helping out. This superb job, and thank you everyone for the winners, the donators, and you remember no regifting, folks. Except that Telrad, had my eye on that one. We'll talk later. Well, that brings an end to tonight's festivities. I'd like to thank Algonquin College and Chef and everyone behind the scenes there for a fantastic meal. And I'd like to thank you folks, the audience, for making our dinner a very special one. And of course, our special guest, Dr. Irwin. Thank you very much for an excellent talk. So that brings tonight to a conclusion. Remember the calendars, the 2014 calendars are still for sale. One for 16, two for 30 at the front door still. Great. Our next meeting here's the calendar now. Our next meeting is Friday, December 6th, 2 weeks from tonight at the Science Tech Museum. It'll be streamed online again. Number 2, for sure. But we'd like to see you there because the December meeting is the semi-annual swap table. So if you have stuff to buy, want to buy, stuff to sell, astronomy-wise, no spouses, leave you there, no spouses, come early. It starts about 7:30 for a swap table.
And come with your ISON images.
Yeah, ice and images, yes. And Lovejoy, too. Just as good. So that's it, folks. Drive safely, please. And see you, next Friday, or if not, 2 weeks from now, or if not, next year in the same hall. 3 weeks from now. Sorry, 3 weeks. Thanks for correcting me. Thank you. Okay, folks, thanks for coming. Good night.